Okay, excellent. I will start. So thank you very much for joining. I'm Daniele, one of the instructors at Learn Kubernetes. Today we're going to talk about requests and limits in Kubernetes. So I'm going to share my screen and I'm going to start the presentation so we can get going. Share, and this is my deck. Okay, so few words about who I am, who I work for. I work for a company called Learn Kubernetes. We are a company that run courses about Kubernetes and helps other engineers like you learn Kubernetes. My name is Daniele. People call me Daniele, Daniele, Dan. Um, someone, I've got a friend making fun of my name, calling me D5E, but we'll get to that into that maybe a little bit later. I had the privilege to speak at KubeCon twice, um, and I was one of the first 500 CKA, um, 500 engineers who obtained the CKA back in 2017. And yeah, most of my day is about teaching and running workshops. That's what I do. And this gives me the opportunity to listen to the students and sort of gather feedback and sort of insights on what's really difficult. But sometimes we don't talk about. And request and limits is one of these difficult things that, a simple question such as what should be the request and limits turns out to be a very complicated subject. So, and that's exactly what we're going to cover today. We are going to cover some of the intricacies of setting requests and limits. Okay, but before I start, we need to sort of set the scenes and explain what kind of problem we're trying to solve. And to do that, I want to take you back for a second to how the Kubernetes scheduler works. So generally, what we want to do is we want to create a deployment. And what we do is we go and we write a YAML definition with a pod template, and we specify what containers should be running inside the cluster. Now, we type kubectl apply, and this specification is then sent to the API server. And inside the API server, there are different blocks doing different things. But essentially what happens is you go through authentication, authorization. There are a few steps in between, and then eventually this resource is stored inside etcd, the Kubernetes database. Now, once the deployment is stored in etcd, that's when things get a little bit more interesting. And then we've got a second component called the controller manager, which is a bundle of several controllers together. And what it will do will basically be, will be notified of the change, will be notified of this new resource, and it will basically trigger two controllers in sequence. The first one is replica set controller, so the deployment will create the replica set, and then the replica set controller will be notified of a change and create the pod looking inside the replica set specification. So all of these happens behind the scenes, so you don't really see it. You just submit the deployment, and then at the end of the process, you get two pending pods inside etcd. But the controller manager will basically fill in the gap and add this extra structure that you don't see. Now, when these pods are created this pending inside etcd. They also added to the scheduler queue. And the scheduler, the basic job of the scheduler is to figure out where these pods should be allocated inside the infrastructure. And what I mean by that is basically, okay, I've got several nodes in my cluster. Where should this pod go? And that's basically the answer that the scheduler is trying to find. And then the scheduler will find that answer by going through a series of stages. And the main two stages are basically filtering and scoring. So we'll basically consider all the nodes, filter out all the nodes that are not applicable, and then try to score from the best to the worst the remaining nodes. At the end of that process, you basically are left with a list of nodes that could be where you could allocate the pod. Now, let's have a look at how this process actually works in the scheduler, because this is where requests and limits come from. So generally, the problem that we're facing is that when the scheduler does this filtering and scoring, it doesn't really know how much memory and CPU the application is using. And if you think about it, it makes sense. The application is not running, it's just about, we're deciding where it should be running, but it's not running itself. It's not running at the moment. So there is no way for Kubernetes scheduler to basically say, okay, this is using 1 GB of memory or it's using 1 CPU. So it doesn't really know what's the size. But we can fix that by providing these values to the Kubernetes scheduler. And the Kubernetes scheduler can look at those and basically decide where this spot should be allocated inside the infrastructure. And this is what we call basically requests and limits. So the requests are what we give to the scheduler, and then we will see limits and how they work. So generally, I've got requests and limits are applied to containers, so to processes. So if a pod has got 2 containers, then I will have requests and limits written down twice. In this particular case, I've got a container which has got requests of a quarter of a CPU and 512 megabyte of memory. That's basically what I define as a request. And then next to request, I can have limits, and that's basically how much memory and CPU my container can use. And in this particular case, then I set the limit to 4 gigabyte of memory and 1 CPU. The actual process, so when I launch this application, the actual process could use more memory than what I define in the request. You can use memory and CPU all the way up to the limit. I could use also less memory than what I define in my request. Now, it is important to understand how these memory limits requests, CPU limits requests work, because they really affect how Kubernetes works, and then utilization inside your cluster. And to explain that, I would suggest we start with the memory limit, which is perhaps the most, it is the easiest to tackle, I guess. And the memory limit is basically just a way to define the max amount of memory that a process can use. And in this particular case, I defined the max amount of memory as 4 gigabytes. So if I were to use more than 4 gigabytes of memory, then what will happen next is that the kubelet will basically stop this process. This is quite convenient because there are several cases where the memory could grow unbounded. And a good example is, for example, a memory leak. If your application is having a memory leak, this is an example, the memory leak will basically start using memory. And then when the kubelet detects that there isn't enough memory on the node, what it will do, it will basically just start evicting low priority pods to make space for more memory. And it will evict more pods, and then the application which has got a memory leak will use those new memory to actually grow the memory leak. So eventually, it will just push out all the pods from the node until all the memory is exhausted, and even the pod itself will be evicted. So the memory limit is something that we use to prevent this sort of scenarios, because we don't want the memory to grow unbounded. So if there is a memory leak, it will basically take down the entire node. Does the same apply to the CPU limit? This is where things get really tricky. The difference between memory and CPU is that when we talk about CPU, the way it works is we basically say we allocate a quota over a period. So we could say over a period, I want to set like half a CPU. And that's basically in that 0.1 seconds, then you have to use that half a CPU or 1 CPU, whatever your limit is. If you don't use it, then that amount of CPU is wasted. You will not be able to get it back. And or if you exhaust it, then you will need to wait for the next period to use more. And this sort of creates all sort of complexity, because first of all, you can use this quota anytime during that period. Right? You can use it at the very beginning, you could use it at the end, in the middle. And the other tricky part is that if you were to use more than what you were allocated, then the process will basically be paused. And then the excess CPU you need to process your API request or whatever you're doing will need to be processed in the next period, which basically means that sometimes your application will basically be paused and then resumed in the next period. Now, this is very annoying, and I'll show you with an API request. So imagine that you have deployed a Java Spring Boot application, and then you've got users calling an API endpoint to return some sort of JSON structure. And imagine that there is a call in the database, you're doing some pre-processing, so on and so forth. But your memory limit is, your CPU limit is very, very low. So what happens next is the request comes in, and we want to process this request, but we don't have enough CPU to actually convert this payload into a different structure, for example. So what will happen is Spring Boot will try to process the application, doesn't have enough CPU, and it will be paused. And then it will need to wait for the next period to actually go and do the work. Now, we talked about this period being a fraction of a second, and you might say, well, it's not that long, right? I would barely notice that. But the reality is that this could happen several times in this period, right? So if your limit is very, very low, then the application will constantly go, okay, I'm doing some processing, pause, doing some processing, pause, doing some processes, pause, until finally it's done and returns a response back to the user. So what you will basically experience is that the application takes a long time to complete the response and returning back to the user. Now, it gets even more complicated because what I show you right now is just an application using a single thread. But imagine that your Spring Boot application has got a server and can run several threads simultaneously. In this particular case, I've got 8 threads consuming CPU at the same time. So what happens is, let's assume that my limit is 1 CPU and each block is a tenth of a CPU. Then in this particular case, what we're doing is we are allocating fairly this amount of CPU to all threads. But 6 of these threads, 2, 4, so 6 of these threads are not able to use 200 millicores of CPU. So what will happen is if all of them were to use 200 millicores, then 6 of them will need to wait for the next period. Now, why is this important? It's because sometimes what it could happen is you have 8 threads and you have a limit. And what it will do, that it will be one thread using all the CPU available. And then it wouldn't basically let the other threads have any chance in processing the request. And what you will experience on the other side, so the user using the application or just this JSON API, is that some endpoints return immediately, but others takes a little bit longer and it's very unpredictable. And that's because some of the threads will basically starve the rest, and basically just one at a time will actually work. All the others will need to wait for the next period to make this work. So generally, setting CPU limits is tricky for this reason, but there is something else that you should be aware when it comes to CPU limits and in Linux, I guess. I think I want to say Kubernetes, but it comes down to how Linux kernel works. So imagine that you have a one CPU node and you use a container which uses 200 millicores. Then you have a second container which is using just half of the after the CPU request of the first one. And so my question right now is, what happens? So I would assume CPU limits will protect me from having a container just using all the available CPU on the node. And that's basically the reason why I would like to set the CPU limit. But it turns out that if one container uses all available CPU, then they will be able to use all spare CPU and not the actual request. And this is because when you define requests in Kubernetes, whatever that is, memory or CPU, these values are basically guaranteed to you. So you're basically saying, I want 100 millicores of CPU, then no matter what you do, then Kubernetes will basically reserve that amount of memory from you. Now, if you don't set the CPU limit, then what it will do is the process will use all available CPU. However, it will not go and eat into the 100 millicores that were guaranteed to the other container. It will just use whatever is left available, which is usually good. Now, what happens if both containers were to use the same, 100% CPU? In that particular case, then what it will happen is that the ratio at which the spare CPU is reparted will be based on the ratio of the request. So since the ratio is here is 2 to 1, then the container will basically divide the spare available CPU between themselves with a 2 to 1 ratio. So the total will basically amount to 66.6 and 33.3%. Um, so overall, it's a fair reposition. Now, setting these requests and limits, it's got consequences, like several consequences to, and that's basically where things get more complicated. So the first consequence is that when you define requests and limits, you can decide to have requests equal to limits. Um, you know, and if you do that, then what Kubernetes will basically assign a quality of service class to your pod. Now, quality of service classes are important because they affect how we schedule and how we evict pods inside the cluster. So generally, Kubernetes will go through and it will try to evict quality of service classes from the least important to the most important. The most important being the current guaranteed class. So when you set limit equal to requests, that you're basically saying, okay, this is the amount of memory and CPU that I'm going to use. So the request helps me guarantee a set of memory, and then the limit will basically just say, this is the max I'm allowed to use. If you do that, this is generally like something you can do, but basically means that if your actual resource utilization is a lot less than what you defined in your request, then because this request is guaranteed, you're basically wasting all of these resources, whether you're using them or not. However, at the same time, this is the class where, if it were a pod to be evicted in the node, this is the last one to be considered. So it's quite safe. So what kind of workloads you should run in guaranteed quality of service? Generally, things like databases, I would say, or stateful workloads are probably a good candidate for this kind of class. The other class which you probably use all the time is called burstable. So burstable classes are basically all the classes where you define at least the request and sometimes the limits. So there is some definition. So we know how big this container is. We know it can probably expand, and we probably have a limit for how much it can expand, and so on and so forth. Now, the good things about this burstable is that we define, sort of how big they are, but we know that they can grow. The issue with growing is that what if all of them were to grow at the same time, right? And that will basically lead to an oversubscribed node, which in turn will probably trigger the autoscaler. So there will be some eviction because not all the pods can stay in the same node, and that eviction will basically trigger the pod autoscaler. So this is the most common way to run workloads. So this is quite normal. The last kind of class is called best effort, and it's something that you should hopefully never use. Best effort is basically when you don't define any limits, any requests or any limits on your containers. When you do that, then Kubernetes isn't exactly sure how big is this box that has to be placed inside the nodes. So it will basically just count the numbers, as simple as that. And it will basically assume that you can deploy as many as you want. Well, of course, there is a limit on the number of pods you can deploy in a node. That's usually between 110 and 250. But the idea is that Kubernetes doesn't know enough about this application to allocate it properly. So we'll just try its best effort in doing so. This is generally something that you should avoid as much as possible in your deployments. Now, we talked about quality of classes, we talked about requests and limits and how they basically work. What we also talked about is, the actual memory and CPU usage of a container could fluctuate all the way to the limit, but it could also be lesser than what you define in a request. And this is perhaps where things get very interesting from a point of view of utilization. So most of the time, what we want to do is we want to deploy workloads in a cluster, and we want to utilize these nodes as much as possible. So I'm talking about utilizing all the memory, well, utilizing all the CPU available in our node. So the first things you need to remember is that every time you define a request, you're basically guaranteed that you will get these resources, right? This Kubernetes scheduler will make sure that there is enough memory, there is enough CPU on that node for you to run. But what happens if the actual usage of the application on average is below the request? Well, it means that whatever else you define in a request, it goes underutilized. But this is something that no other pod can use, no other process can use. So effectively, these resources are just wasted. You're not using them. Now, if your request is 4 GB of memory, for example, and the actual memory usage is half of that, then you've got 2 GB of memory, which are basically not usable by anything else inside that node. Now, what about the opposite? What if you actually set the request, but you are a little bit optimistic and the application uses a lot more than what you defined? Okay, so that's the opposite scenario. Well, what it will happen is the application will basically be a little bit bigger than what you define. Of course, Kubernetes will try and find a node for you. It will assign that node to the pod. But because this pod is actually a little bit bigger than we anticipated, it might be that actually it cannot really fit in that node, and it might trigger an eviction, which isn't great, because an eviction could also trigger an auto scaling, and this could lead to one, oversubscribing nodes, and two, quite a lot of scaling up and down with the cluster autoscaler. So opposite example of what we did just now. So if we've got a 4 GB of memory request, but my application uses, idle 6 GB, then I'm oversubscribing, overcommitting that particular node. So generally, this is something that you don't want to do. So either way, if we underestimate or if we overestimate, we still have the problem that these requests and limits sometimes are too problematic. Let me just take a pause here, and let me see. Okay. So someone mentioned that my microphone is too low. I don't know what to do about this. I was not prepared. I was not prepared. Let me. Yeah, I think it's max. Not sure. If this is on LinkedIn or YouTube, let me know. Just to sounds both on. Okay, I'm sorry, guys. I'll do it better next time. So to recap, I think what you want to do is, most of the time you want to always set the requests. That's definitely going to help you to define the guaranteed sort of memory and CPU usage you want to have for your application. You should always set the memory limits, because if you have a memory leak, then it's fine. You've got a way out. Maybe you don't always need CPU limits. I would say most of the time, maybe, because even if the process is going to use 100% CPU, it will not affect the other pods. So basically, you're saying, okay, if there is enough CPU, you can go and get it, but please don't touch the others, and that will work. Now, when you define request and limits, then those will affect your quality of service classes, and those are used for scheduling and eviction. So by the scheduler and kubelet in your cluster. And then we talked about these requests mismatch. So we talked about these requests because some resources are guaranteed, and if you set them too high or too low, then they have an effect on how you on the utilization of the node. Now, I was very ambitious. I wanted to cover something else, but I'm going to jump and to the next topic, which is basically, okay, now we know memory and CPU requests and limits. So how do I actually choose the right value for requests and limits? And so if, of course you could guess, maybe you have a good understanding of how the application works, and you can say, this is 2 GB of memory, one CPU, I'm done. Then you can do a little bit less guesswork. You can rely on tooling. And I've got two toolings to show you. And then we're going to take this to the next level. And we're going to discuss how to do it dynamically. And I think this is where the discussion becomes a little bit more complex. So let's, most of the time what we have is an application. And this application has got a memory and CPU profile. And what I mean by that is that depending on how much traffic you generate, or depending on what your kind of workload you're doing, then the CPU and memory will go up and down. So what you could do is you can install something called the vertical pod autoscaler, and the vertical pod autoscaler will basically measure the CPU usage and this memory usage, and will record and store these values so it can be later analyzed. And when I say analyze, we're basically deciding, on average, how much memory is my process using? What is actually the correct value for this time period? So this is what the vertical pod autoscaler do. Actually, there are two modes. There is the let's say the analysis mode, where you will record all this data, and then there is a different mode where will actually change the value. So if you were to install the VPA right now and you were to run it, what it will happen is that the vertical pod autoscaler will give you back some numbers on where it thinks this memory and CPU usage is. And you can use this number to set the requested limits. Now, there is another tool. I mean, VPA is one tool. There is another one called Kubernetes Resource Recommender, or KIR, and that works similarly. And what the difference between the two is that KIR is a CLI, which connects to Prometheus. And so you would normally have Prometheus monitoring your cluster, collecting metrics from your pods. KIR will basically connect to Prometheus, and it will basically get this data and basically run some sort of analysis to figure out which CPU limits, which CPU request should be changed, and the same for memory and memory limits and requests. Now, most of it, for until this basically was me maybe a couple of months ago, and I will basically stop the streaming here and say, this is it. But I think something changed. Something's changed in the past few months. And I think this is perhaps the reason why I wanted to run the webinar, and I wanted to share what I learned. What I realized, so there are basically two podcasts, well, a few more episodes of CubeFM, which really struck me. So the first one was from Kensei. And Kensei basically shared his story about how a company called Mercari is scaling requests and limits. And initially what he said is basically that they had like a very rough prototype that would basically recommend CPU and limits to developers on Slack. Like you see right now, this is basically a Slack message saying, hey, your app is requesting this amount of memory, this amount of CPU, you should change it. And it was basically based on the VPA. And then what they found out basically, and I recommend you to go and watch the episode, but what they found out is basically the developers didn't have time to go and change it. And these changes will be like, not just you said it once, but it will come back, right? Every day it will basically be like, oh, can you adjust again? Oh, can you adjust again? And this didn't really scale. So what they basically did was they took a step back and said, okay, there are basically two dimensions we can work with. We can increase the size of our pod. That's one dimension. And then the other option that we have is, instead of increasing and giving more memory and CPU, we can create clones, right? And that's basically the work with the horizontal pod autoscaler. So the horizontal pod autoscaler will create copies. The vertical pod autoscaler will be increasing this block and giving more memory and CPU. So they said, what if we combine the two, right? What if we actually find a way to collect all of these metrics and instrument the VPA and the HPA together so they can basically scale in both dimensions at the same time? They call the word project Tortoise. And basically the way it works is you've got a CRD, so a custom resource definition called Tortoise. You basically explain what kind of policies you should use for your containers. And what it will basically do is it will basically look at the application usage, and based on the metrics, it will basically say, oh, okay, I see a spike in CPU. Okay, I'm going to create more copies. Okay, I see a spike in memory. I'm going to create bigger boxes. Okay, so the memory and CPU are stable. I'm going to keep it like that. The memory goes down, the CPU goes up. I'm going to resize these boxes to make it smaller, but I'm going to increment the number of them. And this is to better utilize the memory and CPU. So this is dynamically adjusting the size of the pod and the number as well. Now, there is another episode which is not has not been released, and it will be released soon. Which has got another company which you probably know, ByteDance. And what they've done is they've taken things to the next level. And when I mean next level, I mean they basically created a system called Catalyst, which is a way for managing quality of service classes, resource recommendation, oversubscription, and overcommitment at scale. And we're talking about a very large scale here. But what they have done, they have basically figured out a way to overcommit nodes. So basically, when the Kubernetes API will query the node, then the node will report more memory and CPU than is actually allowed. Um, why, if you were to picture that, it will look like this. But why would you do that? Why would you overcommit your nodes? Now, if you were to go back and see, so what they basically describe is that when applications developers use the cluster, they tend to overestimate how big this application is going to be. So on average, all of these deployments actually use more memory and more CPU than they actually need. So to compensate for that, they basically oversubscribe their nodes and just monitor whatever is going on inside the cluster. So in this particular case, this is what they're trying to solve. They think most of the people are just setting requests which are way too high. So they are faking the node, and they are making sure that it's actually reporting bigger size than it should be. But how is that a good idea? Well, they basically have a fixed overcommitment, which I just showed you, but also dynamic, basically on how these resources are submitted to the cluster. Then they've got another component called KIR, which is very similar to what we just discussed, which recommend resources and and how it works. So let me show you how it works. So we basically have like they created a wrapper around the quality of service classes of Kubernetes, but those are way more specific and way more, I would say, way more specific around how CPU works. And on top of that, they've got like a system which is connected to the kubelet. I don't know how. I haven't figured out yet how this works. But basically, this system collects metrics from the kubelet and also fake the size of the node. So a node could be overcommitted and could report more resources than are actually available. The combination of two and these resource profiling, so the resource recommender will basically do is will give them an idea on how oversubscribed is in the entire cluster. And on top of that, they've got also a special sort of operator which will basically go and consolidate nodes. So they basically divide their workloads into online and offline. So offline could be something like something that we done in the background. And basically they have node pool for online and offline workloads. And this basically controller will continuously shift stuff around in such a way that all the pools with offline workloads would be running offline workloads, and the same for online workloads as well. So all of this done to maximize the efficiency and resource utilization inside the cluster. So we're talking about very high number here, though. So 20,000 nodes and up. So they basically designed this to optimize the utilization. So I'm really looking forward to be honest, I researched this, but I'm really looking forward to the episode when it comes out. I think it will be really nice to explore how this all works. So we talked about four things today: vertical pod autoscaler and KRR. So both of these two are sort of, so KRR I think is the most static of all of them. This is my perception. Whereas vertical pod autoscaler will basically adjust the values as you move on. Tortoise is a combination, is taking basically a vertical pod autoscaler to the next level. You're basically just analyzing this data and deciding how to replicate the pods and how to make them bigger. And then Catalyst is basically these idea taken to the extreme. How do we actually wrap all these quality of service classes to create even more complex? How do we overcommit nodes to ensure we have enough, um, we allocate resources at the right level? Now, this still leads me to, to what I learned. So if there is something, this has been a research for quite a while now. So I've been researching request limits, node size. I've published a calculator on how to size nodes as well. I've been running this for maybe 3, 4 years. And I think just in the recent past, I think what I learned is that, my assumption was request and limits are something you set and forget. But what I learned is that you can't do that. You can't just set it and then you're done. Because the application that we deploy in the cluster, they change continuously, and they change also based on the load that they get. The requests and limits are basically never right. So you need to continuously go back and amend the value. And while you can do this manually, I think you could probably do it manually just for a couple of apps. But if you're doing it at scale in production, I think you need to find a way to do it programmatically. That was basically my takeaway from some of these, some of the episodes I watched on KubeFM, some of the latest sort of products I see on the market. The other things which I learned is that these requests and limits have got they affect quite a lot of things. So we talked about quality of classes, but also the node size. So if you think about a recent, other tools like Carpenter, for example, so all of these requests and limits will basically go down and and touch everything else that is to touch in the cluster. So while you might think that there's something simple, something that you can set and forget. Actually, they might be the reason why you're spending so much in having like 10 nodes or 100 nodes. Maybe your request limits are not properly set. The other things which I learned, and I'd love to dig deeper in this, because I don't think we as a community we're covering this enough, is that all of these sort of systems that analyze the state of the application and derives metrics, like the VPA, for example, how do they account for memory allocation? If you're talking about Java, for example, or garbage collected languages, then this memory is only collected when the garbage collector will basically decide to do so. So they could basically go and ramp up the memory usage and then collect at the end, or they could be more aggressive. How does that affect the VPA, right? Is anyone doing this? I don't know. This is something like I'm really fascinated about it, but I haven't found the answer yet. And the other one, which we sort of already discussed, is there is never a right request or limit, a request CPU or memory. They change all the time. So you definitely need to have like something in place that changes this value for you, or at least gives you an idea and you can go and change it. But at the scale we're talking at, you need to have something automatic. I think that's the way to go. And then the last question I haven't figured out myself, and I hope someone from the audience will reach out and say, hey, I know the answer, is, did we have all of these problems where we have VMs, virtual machines? Why do we have all of these problems now? And if we have the same problem with VMs, how do we fix it? I just find it fascinating that we have all of these problems with Kubernetes, but I don't want to repeat the same errors maybe we did in the past. So maybe it's about learning how we already solved in the past. So I don't really know what's the answer to this. But if you do, please let me know. I'll be happy to learn something new as well. That's I know it was a lot. Hopefully, some of you are still online. Maybe the microphone's wasn't working very well, but I hope you enjoyed. It was definitely quite a journey for me. I still have a lot of questions I want to get answered, but hopefully you found this useful. So if you're looking for me, you can find me on LinkedIn or Twitter. I run a bunch of workshops from time to time. If you're looking for a Kubernetes training, just visit Learn Kubernetes. And then I also publish a newsletter every Wednesday on Kubernetes, what I think are the best articles for learning Kubernetes. So that's called Learn Kubernetes Weekly. And you can subscribe to this URL. And if you're interested about a VPA and how it works, so I wrote like a white paper with Ellie from PerfectScale. So Ellie showed me like the quite a lot of cases where there are limitations in the vertical pod autoscaler. And so we compiled together like a list, and we analyzed, and we wrote also a flow chart to basically help you guide on where you can use the VPA and when you cannot. So I think there is definitely a lot of research needed, um, in the community, in the tooling, because VPA somehow is limited, but that's basically one of the main projects we've got. Yeah, so I think that's pretty much all I wanted to share with you today. So I know I know the microphone doesn't work very well, but I'll try to see if there is um, any question in the chat, and I will try to answer them. Yes. Okay, there are a lot of people complaining about the audio, but I don't think I can do anything, anything about this. Okay. Let me just. Okay, I can see there are some questions, so I will try to answer the questions before I leave. So the first question is, would you recommend using the approaches applied in production, or is this something to do non-prod to get the limits and send them in prod? I think this is a good question. So let me rephrase that. So should you use the VPA just in lower environments like test and staging, and then you get the value and then put it in production? I think I wouldn't recommend this. And the reason is because production might have a completely different sort of pattern in traffic and usage. So you will get the value from staging and then pass them to production where they are completely different. So I think when I talk about setting requested limits at scale, I'm actually suggesting you should do that in production. At least that's the perception I've got based on my research. So I've got another questions. So there is an interesting question about your use case. So Alfred is saying it has a machine learning pipeline, and the pipeline fetches some data, and then the next component in the pipeline should be resized accordingly to how big the data is. Yeah. I, I think these kind of workloads, I mean, I don't know a lot of the details, but I suspect this, if it is like a job, you could probably create an on-demand job with different requests and limits. But something else that we have in Kubernetes that could be an option is in-place pod resizing. So this is a new feature that has been released in Kubernetes, not fully usable yet, but it will basically just increase the size of the pod at runtime. So whereas the VPA can do that, it can only do that by restarting a container, restarting a pod, so deleting it and creating a new one. In-place pod resizing can do that at runtime. So I think that could probably solve some of this, but I think to answer this question, we probably need to look at the app. There is another question saying, would you recommend to always set upper limits to your pods? So we covered some of this already, and my suggestion would be always set the limit for memory. And then for CPU, I would suggest maybe not. So we talked about how these setting CPU limits can affect latency. Particularly if you've got several threads running in the application, you don't really know how these threads are going to consume, how quickly you're going to consume the limit. And that consumption could actually lead to unexpected latency. However, sometimes you're like, the reason why we have CPU limits, I mean, it is a little bit tricky to explain, but it boils down to you really want, you're basically a cloud provider, you are assigning a CPU limits to one of your tenants, and you're billing based on that. And you might have the similar scenario in your company, maybe, I don't know. You're basically giving away namespaces and saying, This is the amount of memory, this is the amount of CPU you're allowed, no more than that. Then in that case, setting limits on CPU is okay. Of course, you might encounter some of the scenarios we talked about, some of these unexpected 99 percentile latency because one of the threads is um, using all available CPU. Cool. So we've got another questions. By the way, I'm taking the questions from YouTube because I cannot figure out how to do it from LinkedIn. But someone is basically asking any comment about setting request and limits to the same value. So I think these questions um, is related to quality of service classes. So we talked about 3 quality of service classes. So guaranteed, burstable, and a best effort. So what happens is sometimes what happens is a pod is scheduled and that pod could be um, growing in size. So let's say it's a pod is burstable and that pod grows in size and then there isn't enough space in the node anymore. And the kubelet will have to decide which pod should be removed to make space for the others. And that decision is not done at random. There are 2 things that come into play. One is quality of service, and the other one is priority. So in Kubernetes, we've got both. They work so, in, together. But basically, what will happen is the kubelet will look at a class and will look at a priority, and then decide to evict the pod with the lowest priority, lowest class. So what will happen is if you have 3 pods, a burstable, a guaranteed, and a best effort, and then one of the 2 is using too much memory, then the first one to leave will be the best effort. Then the second to leave will be the burstable. And then the last one to leave will be the guaranteed. So I think in that sense, if you don't want the pod to be evicted, and you generally don't want that if the pod is actually, it needs to be local to the node. Like most of the time, I don't want a database to be moved. Then in that case, perhaps I would consider doing a guaranteed. That is my thinking about that quality of service class. So there is another question. This is this is a very difficult question, and the question is it fine to automatically scale horizontally or vertically? So is it okay to use the VPA and HPA in combination with Carpenter? And Carpenter is a special autoscaler which basically sort of estimates the overall. Well, it doesn't do it by itself, but it basically will look at the overall usage requests of pods, and will basically provision a new node that could help you autoscale the cluster. And the question is basically, should I combine all these 3 things together? So should I combine the HPA, the VPA, and Carpenter together? So I think the answer is it probably depends. I guess, not probably the answer you're looking for, but I think it probably depends on what you're trying to do. My thinking right now is that, combining HPA and VPA, it makes sense if you want to automatically set these requests and limits. Good. However, my next question would be, how frequently does this change, and what kind of workloads am I deploying? Are these workloads mostly, are they changing all the time? Are they changing less? Because if I change all the time, then I would expect them to be restarted quite frequently. If that is the case, then we'll probably inform my decision about what to do with Carpenter. Because Carpenter, what it would basically do, it will try to provision a new node where all the pods can fit and so on and so forth. But depending on how quickly it does that and does what we call consolidation, then there could be a lot of pod being destroyed and redeployed in the cluster. Now, this is not necessarily bad. but it might create quite a lot of opportunity for things to go wrong. So it's something, one of the cases which I think really struck me when I talked to Eli is that you need to be really careful about the vertical pod autoscaler, because if 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 the pod a vertical pod autoscaler is going to resize one of the pods, but the other are still there, then you will have a pod which is bigger than the others. And when you debug it, you basically don't know why it works on one or it doesn't work on the others. So in a way, I think his advice was you want to have these pods as predictable as possible. And my take from that was you want to keep it as simple as possible. So you want to have them all of the same size. Maybe you want to increment the number, but you want to be careful about continuously deleting them, recreating them, because there could be a chance that some are bigger, some are smaller, because they're still in between this process. So, I don't have an exact answer for this, but my thinking would be my priority would be figuring out how to debug it if something goes wrong. That's basically where I would optimize my time. Yes, I can combine all three of them, but what happens if there is an error? Am I able to identify why that pod was in that particular state and it wasn't like, the VPA didn't indicate it bigger or smaller or so on and so forth? So a lot of variables in play. So the other question I've got is, can KIR and Prometheus monitor resource usage at a component level for each run? I think you can. Um, so I tried KIR once, but I know they are developing it quite. They got quite active community. So I would assume you can, but I'm not entirely sure. The only issue with KIR, I think, is that it's a static tool. So it's a CLI you need to run from your laptop, or your computer. I think this is. I don't think this is actually good enough. As in, it is good enough to get a value, but I think based on where my thinking is at the moment is that you need something more proactive and something that works at scale. So running a CLI will give you ideas on how big things should be, but if you want to run in production and you want to adjust these values dynamically, then you need something which is one notch, more sophisticated than KIR. Okay, I've got probably another question. Um, so the question is, in a multi-tenant cluster where different teams have their own namespaces, would you recommend using limit range and resource quotas? Um, Tricky question. So we covered a session about multi-tenancy last year with Loft, and what we did was basically looking at the different sort of different features that you should consider when running a multi-tenant cluster. And we talked about resource usage and costs, of course. And one of the things that we sort of realized is that with multi-tenancies, you have got several we think about multi-tenancy as something like, either you have it or you don't. But in reality, you have like several sort of shades of multi-tenancy. Some are, very loose, some are like very strict, and you have everything in between. So I think overall, my sort of experience is that people will use namespace differently, and so I would suggest, using, yes, most of the time, I would suggest using limit ranges and resource quotas. And in the past, at least for me, those were useful because, I could cross bill other teams in the organization. So it was a very easy way to say, okay, this is your namespace. It's going to cost you X. It's got X amount of memory, X amount of CPUs, and I've got a limit range done. However, this is based on how the company sort of describes and work, and you might have like a more loose structure. Perhaps you don't have as many tenants, and the cost is shared, and perhaps you don't need to go down that route. Maybe you don't need the limit ranges. Maybe you trust what the others are doing. Maybe it's just you and few other teams. Maybe you don't need to go that way. So I would think, in the past, I used to think, yes, always limit ranges, always resource quotas. I think right now I'm taking a more conservative approach and say, okay, how much do I trust my tenants? Um, how much can I get away with without adding more stuff on top? So I would basically, I can put some links in the description, but that's what I would consider before going down that route. So it depends a little bit on how your company is set up. Okay, last question, and then we'll probably end the stream. I think this is a very interesting question. Um, so so Atul is sharing that the biggest issue they face is burst workloads, which are mostly idle, and then they've got like a spike in usage. Um, yeah, I think that the challenge in this sort of scenario is, okay, if I over allocate requests, then most of the time I'm paying for resources I cannot use. So Azul is basically just paying for nothing, right? But if we under allocate the requests, what it will happen is, okay, and any other process can use these resources, but when the process really needs them, they might not be there. Okay, that's basically the challenge that is facing, which is a fair challenge. Um, so I don't. Um, to be honest, I don't know. I don't know the exact answer. I don't know idea. But as everything in life, I guess there is a trade-off, right? So Atul's trade-off, as far as I can tell, I can pay more money, or I can in advance. So that will be basically setting very high requests, and a little bit higher requests to compensate for the spike. Um, and then the other sort of option is to be to set these requests lower, but expect more pods to be evicted and deployed elsewhere. So I think in that particular case, I will basically just figure out a way to over provision nodes. Um, yeah, maybe something like that. Yeah. Either way, I think um, not an easy way out. I would say maybe a dedicated work pool. It sounds like the workloads is mostly would be benefit from something like serverless, where you have like a huge burst and then it goes down. But yeah, I will need to figure out a little bit more about the app. Okay, cool. That was last question. If you got more questions, yeah, you can reach me out on Twitter or LinkedIn. I will try to answer. As I said, this is part of the research I do. It's a very very fascinating topic, and the more I learn, the more I discover I know nothing. So I'm really happy. I've noticed someone mentioned what happened with VM, so I'm going to read it now. So whoever's that was that, thank you. I will Nelson. Thank you very much, Nelson. I will go back and read that. Yeah, that's it. Thank you very much for today. Thank you for tuning in. I'm probably going to do another one of those next year. So yeah, I'm looking forward to see you there. Thank you.